In this video, we're going to use Varignon's theorem to evaluate the moment of forces. Now, say we have a force F, and that force F equals 60 newtons. And that force, let's say it acts at a point A, and that's our coordinate, force 3, and also at some angle of, let's say, 36, I'll just add 0.9 degrees, and this happens above the horizontal. So this here happens above the horizontal, and we're going to have another set of details that O is the origin. So that's all we need, and we can go ahead and start looking at what the theorem actually implies. Now, before we use Varignon's theorem, we must first resolve the force into components. And since the angle is measured from the horizontal, then cosine will give us the horizontal component and sine will give us the vertical component. So what that is really, it's similar to what we have looked at before. So we would have here our components. So fx for our horizontal component, which is f cos theta, which is theta represents our angle. And for vertical components, fy, it's just going to be f sin theta. So what we need to do here now is to really resolve these horizontally and vertically. So that's what we're going to have a look at now. Our force is 60 newtons and our angle being 36.9. So we're going to have here, 60 and cos 36.9 for the horizontal component. And this gives us an horizontal component of 48.0 newtons. And if we do the same thing for the vertical component, then the force remains the same. So our vertical component will just simply be 60 sin 36.9, and we get this vertical component of 36 newtons. So that right there represents our force components horizontally and vertically. Now, Varignon's theorem states that the moment of a force about a point is supposed to be equal to the sum of the moments of its components about that same point. Now, when we apply the theorem, we need to take the moment of each component separately. But there is a trick that you need to ensure that you be aware of, which I'm going to explain now. So let's just make some space and I'll go through that. So the first thing to note is that the horizontal component, it uses the vertical distance. So I'll just make a note of that. Our vertical distance, I'll just put VH for vertical height or distance from our coordinate, which our coordinate was, let me just have a look. Our coordinate is 4, 3. So our vertical distance then will be 3. I'll just say 3 meters. Whereas our horizontal distance, I'll just put HX for horizontal distance. Our horizontal distance here needs to be 4 meters. So just ensure that what we have is our, for the horizontal force component, we use the vertical distance. And for our vertical force component, we use our horizontal distance. And that's simply because the moment of a force is the force multiplied by perpendicular distance. So if we have the horizontal force component, if the force is acting horizontally, then it's the vertical distance or length that would be perpendicular to that. And we've already stated that these are measured from the origin already. So what we have now then is let's take the moment of our force, horizontal force component. So we would just simply do 48 multiplied by 3, and that will give us 144 Newton meters. Taking the moment of our vertical side now, which we got for our vertical force component 36, so it's 36 now being multiplied by 4, and this also gives us 144 Newton meters. Now, in terms of moments, we know that moment is actually a vector, so we need to also establish how these will rotate. So we can see where, if we were to sketch this out and draw your force and the perpendicular distance, this one here would be rotating clockwise. And I'll take clockwise to be positive, and then this next one here will be rotating counterclockwise, and I'll take that to be negative. And in terms of the moment now about the origin, this is just simply summing these force components. So it actually turns out that because these have the same magnitude, we would end up with 144, so that's a positive, and plus another negative 144. So it actually turns out that we have a system in equilibrium here. So that's our final answer. And if these values were different, if we had different numbers for the 144, then it would obviously take on a different sign. But that's the process. That's how you would go about solving these. And if you found this video interesting, you might also want to check out this next concept right here.